Hello students, today now let's move on to the next theorem. If f belong to R of alpha on closed interval a comma b, and if c belongs to open interval a comma b, then f belong to R of alpha on closed interval a comma c, and f belongs to R of alpha on closed interval c comma b. Okay, so this is what we need to prove. If f belongs to R of alpha on closed interval a comma b and c is any intermediate point, then f belongs to R of alpha on closed interval ac and f belongs to R of alpha on closed interval cb. Okay, this is the first part of the theorem. And the second part of the theorem is that integral a to b f d alpha is equal to integral a to c f d alpha plus integral c to b f d alpha. So this is what we need to prove in the second part of the theorem. Okay, now let's move on to the proof. Since f belongs to R of alpha on closed interval a comma b, by the condition of integrability, we have for any epsilon positive, there exists a partition P of closed interval a comma b such that u of p comma f comma alpha minus L of p comma f comma alpha less than epsilon. Name this as 1. So this is as per the definition of condition of integrability. So now let P star equal to P union this singleton set C. So what we are adding to this partition P, we are adding one more element C, okay, and we are making that set as P star. Okay, so now P star is equal to P union singleton set C, where C belongs to open interval a comma b. Let P1 be the partition of a comma c. So we need to prove f belongs to R of alpha on closed interval AC and f belongs to R of alpha on closed interval CB. See here, I need to consider two partitions, one partition for this interval and one partition for this interval. So here let P1 be the partition of closed interval AC and P2 be the partition of closed interval CB such that P star equal to P1 union P2. So here actually P star is equal to P union singleton set C. And here also we need to look into that P star is equal to P1 union P2 also. Okay, so we can do that. Okay, and here since P star is P star equal to P1 union P2 and P star equal to P union singleton set C. Here P star is the refinement of P star is the refinement of P1 and it is the refinement of P2 also. Okay, since P star is the refinement of P, we have this condition. See, this is from the previous theorem. Okay, so u of P star comma f comma alpha minus L of P star comma f comma alpha is less than or equal to u of P comma f comma alpha minus L of P comma f comma alpha. Okay, actually we have proved this in our previous theorem and you can just look at the previous videos. Okay, and therefore u of P star comma f comma alpha minus L of P star comma f comma alpha is less than epsilon. Why? Because from equation 1 we have u of P comma f comma alpha minus L of P comma f comma alpha less than epsilon. So if this is less than epsilon, obviously this will also be less than epsilon. So I have used equation 1 here and name this as equation 2. Clearly u of P star comma f comma alpha is equal to u of P1 comma f comma alpha plus u of P2 comma f comma alpha. And you need to note that this equation 3 and 4 is not true if if it if it has closed interval a comma c here, and here if it has open c comma b. Okay, since c is closed in both the intervals, the union of these two will be closed interval a comma b. See, you can check this by taking any example. You can check this by taking any numbers instead of a, b, c. Okay, and at last you will get this. U of p star comma f comma alpha is here equal to u of p1 comma f comma alpha plus u of p2 comma f comma alpha. And similarly, L of p star comma f comma alpha is equal to L of p1 comma f comma alpha plus L of p2 comma f comma alpha. See here, p star is actually the partition of closed interval a comma b, and here p1 is the partition of closed interval a comma c, and p2 is the partition of closed interval c comma b. So obviously when you add this, you will get this, and similarly here when you add these two, you will get this. Okay, and here if I subtract these two equations, I have u of p1 comma f comma alpha minus L of p1 comma f comma alpha plus u of p2 comma f comma alpha minus L of p2 comma f comma alpha is equal to this minus this. Okay, so from equation 2 I have this is less than epsilon. So obviously this whole thing, if RHS is less than epsilon, then obviously LHS will also be less than epsilon. Okay, so here this is LHS actually. Okay, so this is less than epsilon, and we know that these two are non-negative terms. Why? Because the difference here is always greater than or equal to 0, but it is not less than 0. And here also the same thing. Okay, see, we know that lower sum is always less than or equal to the upper sum, but not greater than upper sum. So obviously this is a positive term and this is a positive term. So since the above are non-negative terms, we have this is less than epsilon and this is less than epsilon. Okay, so see, if we add these two terms only, we are getting less than epsilon. Then obviously this is less than epsilon and this is less than epsilon. Okay, so at last what we have proved, for any epsilon positive, we have a partition p1 on closed interval AC and we have a partition p2 on closed interval CB, such that u of p1 comma f comma alpha minus L of p1 comma f comma alpha less than epsilon, and u of p2 comma f comma alpha minus L of p2 comma f comma alpha less than epsilon. Okay, so at last we have proved that f belongs to R of alpha on closed interval AC and on closed interval CB. See, actually this is the condition of integrability. So using that, we have proved f belongs to R of alpha on closed interval AC as well as on closed interval CB. Okay, this is all about the first part of the theorem, and we are still left with the second part. Okay, see, this is the second part. Integral a to b f d alpha is equal to integral a to c f d alpha plus integral c to b f d alpha. And we know that, see, actually this is what we need to prove. We know that u of p star comma f comma alpha is equal to u of p1 comma f comma alpha plus u of p2 comma f comma alpha. This is by equation 3. Okay, so now if I take infimum on both sides, I have infimum of this equal to infimum of this. And also we know that, see here, infimum of a plus b is always greater than or equal to infimum of a plus infimum of b. So we know this. So I am using this here. Okay, if I take infimum of this, see, if I take infimum on both sides, here on the right hand side I get infimum of this a plus b. So I can write this as greater than or equal to infimum of a plus infimum of b. Okay, so actually what is this infimum of u of p star comma f comma alpha is actually the upper Riemann-Stieltje integral. So I will write this as upper Riemann-Stieltje integral, and that is from a to b. Okay, a to b and a to b bar, because this is the definition of upper Riemann-Stieltje. Okay, so integral a to b f d alpha greater than or equal to integral a to c f d alpha plus integral c to b f d alpha. Okay, so here we have greater than or equal to. Okay, and here we have integral a to b f d alpha greater than or equal to integral a to c f d alpha plus integral c to b f d alpha. See, instead of that b bar, c bar, b bar, I have removed all this and I have written simply a to b. Why? Because here f belongs to R of alpha on closed interval ab, and if f belongs to R of alpha, I can do this. That is, upper Riemann-Stieltje integral becomes equal to this common integral, that is integral a to b f d alpha. Okay, so f belongs to R of alpha on ab, ac and cb. So I have done this for all three integrals. So this integral now looks like this, and similarly this. So I have got this. Okay, and if I use equation 4 and take supremum on both sides, I will get less than or equal to. Okay, see, I need to proceed in this similar manner, and at last I will get this inequality. Okay, see here. See here, if I take this equation and if I take supremum on both sides, if I take supremum on both sides, I have supremum of this. Supremum of this will be less than or equal to supremum of this plus supremum of this. So that is nothing but the definition of lower Riemann-Stieltje integral. So at last you will get integral a to b f d alpha, that is lower Riemann-Stieltje integral, less than or equal to integral a to c f d alpha plus integral c to b f d alpha, and that is actually a bar. Okay, so here instead of upper Riemann-Stieltje you will get lower Riemann-Stieltje, and since f belong to R of alpha on closed interval ab, ac and cb, I can write this in place of lower Riemann-Stieltje integral. So since f belongs to R of alpha on closed interval ab, ac and cb, in place of lower Riemann-Stieltje integral, I can write this. So at last I will get this. Integral a to b f d alpha less than or equal to integral a to c f d alpha plus integral c to b f d alpha. So using this equation and this equation, I have equal to integral a to c f d alpha plus integral c to b f d alpha. So see here, from this equation we have this is greater than or equal to this, and from this equation we have this is less than or equal to this. So at last, if you take these two equations into consideration, at last we have equal to, and that is the proof of the second part. Thank you.